So, in our previous analysis of the theoretical performance limits, we have found that the error probability of a random code under maximum likelihood decoding is upper bounded by 2 to the power n times the rate of the code minus the term that we called the mutual information I between x and y. Then we have seen that if the rate, and this expression holds for a sufficiently large n. So to be precise, this is for sufficiently large n. We have formalized it with epsilon, with an epsilon delta expression, but for simplicity, we assume that epsilon delta get negligibly small, and then we have a sufficiently large n such that this expression holds. And then if n is large, and this term is negative, the rate is smaller than the mutual information, then the error probability goes towards 0 because the exponent gets negative, 2 to the power minus something very large and negative because n is very large, goes to 0. So we can make the error probability arbitrarily small if the rate is smaller than this mutual information. So now in this chapter, we are going to look at how we can calculate this term, this mutual information, and we're going to look at some common channels to see how the mutual information is actually obtained and what this means, and we call this the channel capacity. This is what this chapter deals, and we will give a whirlwind tour of what is called information theory. We just cover some very tiny aspects, and that will be sufficient for our analysis. So we start with something that you may know from Communication Engineering 1, which is the entropy of a discrete random variable. The entropy is a measure of the randomness of a random variable or measure of the uncertainty of a random variable. And the entropy is defined, h of x, that's what we call the entropy, is minus the sum over all possible outcomes of x of the probability that this outcome happens times the log 2 of this probability. If we look closely, we see that this is the definition of the expectation. So if we recall, the expectation of a function f of x is equal to the sum over all possible x of p of x times f of x. And here, f of x is the probability that x happens, or actually the log 2 of the probability that x happens. And we can then also define the entropy of a discrete random variable as an expected value. It's essentially minus the expected value of log 2 of p of x. And if in this expression we have 0 times log 2 of 0, then we define this to be equal to 0. This is because we calculate the limit coming from positive values towards 0 of x times log 2 of x. This limit is equal to 0. That's why we define 0 times log 2 to be equal to 0. That's the definition of the entropy. So we can say that the entropy is a measure of how unpredictable a random variable is. If the entropy is larger, the random variable is more unpredictable. If the entropy is smaller, it means the random variable gets more and more deterministic. So the random variable is a measure of how deterministic a random variable is also. So let's take a look at two examples. First example, we have an x random variable that is binary. So x takes on values either 0 or 1. And the probability that x is equal to 0 is equal to 1/2. Therefore, the probability that x is equal to 1 is also 1/2. And then we can calculate the entropy. So it's minus 1/2 times log 2 of 1/2 minus 1/2 times log 2 of 1/2. And this is equal to 1. So we say the entropy is equal to 1. And usually we assume that there is a pseudo unit, and we say it's equal to 1 bit, and bit because we use the logarithm of base 2. And we use a second example. We again have a binary source, but this time the source is not symmetric. Probability that a 0 occurs is 1 over 4. Probability that 1 occurs is 1 minus 1 over 4, 3 over 4. And we can calculate the entropy. It's just plugging in the numbers into this expression, and we get that there's an entropy of 0.8. And the entropy is smaller than in the first example. And this is because this random variable is much more predictable. When it's more predictable, the entropy gets smaller. It's like in physics, when you have a system with a high entropy, it means there is a lot of movement, it's very unpredictable. And if the system cools down, the entropy gets smaller. There's less movement, less unpredictability. And here it's exactly the same. So if we have a random variable that is very unpredictable, and this is essentially the most unpredictable random variable, because we cannot say anything if it is 0 or 1. So it has the highest entropy. We're going to see that this is actually the highest entropy that occurs. And then we have the other random variable, which is much more predictable, because the 1 occurs more often than the 0. If we want to predict it, we would predict a 1. Then in 3 out of 4 cases, we would be correct. So therefore, it has a smaller entropy because it is less predictable. Now, the entropy, then you can say what is the maximum entropy, or the entropy is bounded. And actually, the entropy of a random variable, and when the random variable can take 1 out of v possible entries, so x1 up to xv, is then upper bounded. The largest entropy is log 2 of the cardinality of the set, or equal to log 2 of v. So that's the largest entropy. In the previous case, v was equal to 2, because we had a binary random variable. We had zeros or ones. So the entropy was upper bounded by 1. So example, v is equal to 2. That means h of x smaller or equal than log 2 of 2, which is 1. And when do we have equality? So when is this inequality sign an equality? That's when x is uniformly distributed. Uniformly distributed means we have a maximum uncertainty. Every possible outcome happens with the same probability. So it is uniformly distributed, and therefore we have the maximum uncertainty and also the highest entropy. Okay. What happens if the random variable we look at is not a discrete random variable, but a continuously distributed? Then we can define a quantity that is called the differential entropy. Just for completeness, we write it here. And essentially, it is using the same definition of the expected value, but now we replace the summation with an integral. So we call it differential entropy, and we say h tilde of x, because it's not exactly similar. Actually, it can also take on negative values. The previous one can only take on positive values. The differential entropy can also take on negative values. Therefore, we put a h tilde because it doesn't share the same properties than the entropy for discrete random variables. This is something we need to be careful. That's why we give it a different name. We call it differential entropy. That's if x is a continuous random variable, and the definition is the same. So we take the integral over all the values where x is defined. That's the so-called domain of x. So it's a random variable. It doesn't have meaningful outcomes for every possible x. So it's defined only for some x. For instance, we have the average height of a German male person, the example that we already considered, and it can also only be positive, and it should only be larger. It should start at 10 centimeters, for instance, if you have a very, very tiny baby. And therefore, it can only take on values larger than centimeters and say smaller than 3 meters. So that's the domain of x. And then we have f of x times log 2 of f of x dx. That's the differential entropy. So with the entropy, we can also define different quantities. First quantity is if we don't have a single random variable, but we have two random variables that have a joint distribution. And then we can define a measure that's called the joint entropy. And essentially, the definition is more or less the same. So if we have two random variables x and y that are jointly distributed to p of x and y, then the joint entropy h of xy is the sum over all possible combinations of x and y times p of xy times log 2 p of xy. And that's just the definition of the joint entropy. So essentially the definition that we had previously, we just move over to joint random variables. Now if the two random variables x and y are statistically independent, then this means that the joint probability can be written as the product p of x times p of y. And then the entropy h of x and y is equal to h of x plus h of y. So we have the sum of the entropies. And this is something you can actually prove pretty easily. We can essentially do it immediately. So we have h of xy, and this is minus the sum over xy. So this is assuming statistical independence times, I would say this is p of xy, times log 2 of p of x times p of y, where we use the property of statistical independence. So this is equal to minus the sum of xy, p of xy times log 2 of p of x, minus the sum over xy times log 2 of p of y. So applied the product rule of the logarithm. But then we can write this is minus the sum over all possible x times log 2 of p of x. I rearrange the summation and equation a little bit, times the product, the sum of all y of p of x comma y, minus the sum over all y of, sorry, here I forgot something. This should be p of x comma y times log 2 of p of y, minus the sum over all y log 2 of p of y times the sum of all x times p of x y. And now this guy is just by law of total probabilities p of x, and this guy by law of total probabilities p of y, and then we have the result. So that's essentially a quick way to prove this result. So in general, when x and y are not statistically independent, then h of x comma y is upper bounded by the sum of h of x plus h of y. So if there is some statistical dependence, the uncertainty of the joint distribution of x and y is smaller than the uncertainty of only having x and only having y, because x tells us something about y if they are dependent, and this little bit that we know decreases the uncertainty and hence decreases also the entropy. So then we can define the conditional entropy, and the conditional entropy is essentially the same concept, but based on conditional probabilities. So again, we start with a random variable x, and we have a random variable y that is conditioned on the observation x. So x is some observation, and we have a random variable y that is conditioned on x. So then we define, so this is the definition, the conditional entropy of y given x is the sum over all possible x, the probability that x occurs, times the entropy of y given that a specific x has occurred. So this is h of y given that this specific x has occurred. So we calculate the conditional entropy given that a specific x has occurred, and then we average over the probabilities that this specific x even occurs. So if an x occurs very seldomly, then this contribution is small. And h of y given a specific x is defined as we know it. So this is essentially, this guy is h of y given that a specific x has occurred. And then this is just the minus the probability of p of y given x times log 2 p of y given x. And then we have this summation over p of x. And then what we can do is we can take these two guys, and using Bayes' theorem, we can put them together as p of x comma y. So that's how we can calculate the conditional entropy. So it's the sum over all possible combinations of x and y of p of x comma y, so the joint distribution of x and y, times log 2 of p of y given x. And then we can define a chain rule. So the chain rule is saying that the joint entropy is the conditional entropy h of x comma y plus the entropy of y, or it's the conditional entropy h of y given x plus h of x. And that is because of Bayes' theorem, essentially. When we use Bayes' theorem, p of x comma y is equal to p of y comma x given x times p of x. We put this into the logarithm, then the product becomes a summation. That's how you can remember this chain rule. But it's essentially just the application of Bayes' theorem. And then we also have something very important that says that conditioning reduces entropy. So h of y given x is always smaller or equal than h of y. And this also logically makes sense, because if we have an extra observation, the uncertainty becomes smaller of a random variable. So we can think of, if we observe a person, and if the person is very tall, so we observe the height of a person. If we don't know the gender, we have a broader variety, but if we know the gender, on average, males are usually taller than females. So if we know the gender, then we have less uncertainty about the height of a person. So therefore, if we have a condition, if we have some extra observation, the entropy is smaller or equal than h of y. Can also be the case that x does not give any extra information. For instance, if y is the height of the person, then if x is the probability that the sun shines, sun shining has no effect on the height of a person. So therefore, then it doesn't change the entropy. Therefore, we have smaller or equal. So it can happen that the entropy is decreased, but it's not necessary. It depends on how dependent these two random variables are. So that's the entropy. And now we can define the mutual information. that we already have seen. So we can also define the mutual information. We have seen it has an operational meaning. The operational meaning was in terms of maximum likelihood decoding. And now we can define also the mutual information. And the mutual information we saw in our derivation that the mutual information is calculated in this way. So this is what we have derived when looking at the maximum likelihood decoder. The sum over all possible combinations of x and y. Then we have the joint probability of x and y. Then we have the log 2 of the probability of x and y divided by the probability that a certain x happens, certain letter of our code, and the probability that a certain y happens, certain observation. That is what we have derived. And if we look closer at it, and if we simplify this expression, what we get is the following. We get an expression in terms of the entropy and the conditional entropy. So the mutual information is the entropy of x minus the entropy of x conditioned on y, or it's the entropy of y minus the entropy of y conditioned on x. And the mutual information between x and y is the same as the mutual information between y and x, so it is symmetric. And this is another way of calculating the mutual information. So depending on what you have at your disposal, this one or that one may be easier. And we can also express it in terms of an expected value. And this is essentially what we had. So we had this guy in our derivation, and then from the law of large numbers, we said that, okay, this is equal to the expectation. So we went from the other way around. We had our different letters, and then we said, okay, this is equal if n is large enough. This is a sample average, sample mean, and this is equal to the expected value. And therefore, we got this mutual information. So this is equal to the expected value of expression. And the mutual information is something very important, and it's also very important in statistics, in machine learning, and in many other disciplines, because the mutual information is a measure of dependence between two random variables. So if two random variables are independent, when two random variables are independent, p of x and y, the joint probability is the probability of x times the probability of y. And then if we plug this in, so if here we plug in p of x times p of y, then we see that this whole expression is equal to 1. It will cancel. Then we have on the numerator, we have exactly the same as on the denominator. This will cancel. We have log 2 of 1. This is 0. And the mutual information will be equal to 0. So in that case, if x and y are independent, the mutual information is equal to 0. So measuring the mutual information tells us how dependent two random variables are. And the mutual information can also be seen as a reduction of uncertainty due to another random variable. So we have a x, which is our random variable. Then we have another random variable, and this is y, for instance, the observation of x after some noise, and it reduces the uncertainty. The mutual information is large. Y tells us a lot about x. The mutual information is small. We cannot infer a lot about x on y. That's another way of looking at the mutual information. So we can define some properties of the mutual information. The first property is that the mutual information is non-negative. So the mutual information is always larger or equal than 0. Always. Can never be negative. Then we have a so-called chain rule of mutual information. And here it's very important to note colon and the commas. So this is the mutual information between X and two observations, Y and Z. For instance, we have an X and we observe two outcomes of X, Y and Z. So how much do these two Y and Z tell us about X? And that's what we can define using the chain rule of mutual information. That's the mutual information between X and Y, plus the so-called conditional mutual information between X and Z given Y. That means we always have to put a condition on Y in all our probabilities in the expression. That one we may need later on when we're looking at polar codes. For the time being, we can ignore this chain rule. So if X and Y are independent, we have seen already the mutual information is equal to 0. And the mutual information can also be expressed in terms of the joint entropy. So we can say that the mutual information between X and Y is the mutual information, the entropy of X plus the entropy of Y minus the joint entropy of X and Y. This can be easily seen using the chain rule of entropy and just plugging in the chain rule of entropy in the definition of the mutual information. Then we have the so-called data processing inequality. So the data processing inequality says that if X, Y, Z forms a Markov chain, so X is being processed to Y is being processed to Z, so it means formally that the probability of X and Z given Y is the probability of X given Y times the probability of Z given Y. So X and Z are conditionally independent given Y. So it means that also P of Z given X and Y is equal to P of Z given Y. And then the mutual information between X and Y is larger or equal than the mutual information between X and Z, which means processing the data kills information. If we have a system, for instance, we have some X is being processed, then we get some Y is being processed, and we get some Z. Then the mutual information between X and Y, this mutual information is larger or equal than the mutual information between X and Z. And it's clear because processing may kill information. So Z the processor 2 could output zeros, for instance. Then we will have no information anymore. If Z is equal to 0, all information is lost. So processing potentially kills information. Not necessarily, but it potentially kills information. And if it doesn't kill information, then we have equality in the data processing inequality. We say we have a sufficient statistic. And we'll get to that property later on. So we can visualize the mutual information using this well-known diagram. So we can say that we have a source X, that is some data that we have, and X has a certain uncertainty, the entropy. We have some entropy, some undecisiveness of our source. So if the entropy is large, that means also we cannot say so much about our source. It's more random. And then we have an observation Y, that is a so-called sink. And Y also has an entropy. And now we can relate the entropy of Y and the entropy of X using the mutual information. So whenever we make an observation of X, we'll possibly lose information, for instance, because of noise. Because in the transmission there is noise, because we take a picture with a camera of X. So let's say X is a landscape outside. We take a picture with a camera. The camera has a limited frame. It has a limited resolution, so it's pixeled, and we lose information. So we may not recognize what person is in the picture anymore. This is an information loss. That's one way of looking at it. And the amount of information that is transferred between X and Y is the uncertainty of X minus the information loss. That's the amount of information that we actually convey. And then we may looking at it also from a sink perspective. So at the sink, what we receive or what we observe is the information that is actually coming from the source. That's the mutual information, plus some noise. We have the mutual information, and then possibly we have some noise, and this is the so-called misinformation. We either lose some information, and we also get some misinformation. And what we actually convey is the mutual information. That's one way of looking at the mutual information. This may also help you remembering the different terms. So now, with all these definitions, we can actually define the capacity of a communication channel. We have already seen what is the achievable rate. And based on the achievable rate, we can define the capacity. So we said that the achievable rate is equal to the mutual information. And this is because we construct a random code, and we have seen that the error probability, can't stress this enough, is smaller or equal than 2 times n to the power r minus the mutual information, if n is large. So the rate is achievable because if the rate is smaller than the mutual information, the error probability goes to 0 with the random code, and therefore the maximum achievable rate is the mutual information. So now, based on this mutual information, we can define the capacity. So first, we define again the communication channel. We call chapter 1. It's a system where the output Y depends probabilistically on the input X, and it's defined by a probability transition matrix P of Y given X. And now, when we have a random code, n goes to infinity, maximum likelihood decoding, we can achieve the mutual information if the rate is smaller than the mutual information. So now we ask the question, what is the largest rate R that a code can have for a given channel? Is it the mutual information? We have one additional parameter that we didn't optimize. So we calculate the mutual information. When calculating the mutual information, we construct a random code. And for this, we said that P of X I j is equal to 1, or is equal to a certain X is equal to 1 over V. This is how we constructed the random code. Is this a good choice? Well, it depends. This is something that we can potentially improve. We can potentially select a better distribution of our letters in the code words, so to improve get a larger mutual information. And that is the so-called capacity. So the capacity is the largest possible mutual information maximized over P of X. So when we construct the random code, what is the best possible distribution of the letters X so that we get the largest rate or the largest mutual information? And that is what is called the capacity. So we just assumed that this is one possibility, and for many, we will see that for many channels this is actually a good possibility, but it may not be the best one. The best one for this is we need to maximize the mutual information and maximize over all possible probability distribution. You could already guess this is not an easy optimization task. And then once you have this probability distribution, then you can construct your random code according to this probability distribution. And then you can actually go ahead and you can use this code for communication over the channel. So that's the channel capacity. So what does the capacity say? Capacity is essentially the maximum amount of information, in terms of information bits per channel use, that a channel can convey. And if we have a channel with capacity C, there is a code of rate smaller than C, the random code, with which we can reliably communicate over the channel when n is sufficiently large. So when a channel has a capacity of 0.8, it means that whenever we use the channel once, on average, we can convey 0.8 information bits. So it means there is a code of rate less than 0.8 that allows reliable communication over the channel. So we saw the random code achieves this, but the random code is not something that has a manageable complexity. We need to store all the possible code words. When n is large, that's quite a lot of code words. We also need to find a maximum likelihood decoder. That's also potentially very complex. So it doesn't tell us how to realize such a code. That's what we're going to do in the rest of the lecture. But first, it's very important that we understand these fundamental limits, because these will also be used for assessing the performance of a code and to benchmark the performance of a code with respect to these limits. So what is the capacity? And we start with calculating the capacity for a discrete memoryless channel. So capacity of a discrete memoryless channel. So first, we recall that P was the channel probability matrix. So we had P of y1 given x1. Then we had P of y2 given x2. P of P of y1 given x2. P of y1 given x v. Then we have P of y2 given x1, P of y2 given x2, P of y2 given xv, up to P of yw given x1, P of yw given x2, P of yw given xv. So that's how we put the conditional channel probabilities into the matrix P. And then we can calculate the output probability vector. Py is equal to this matrix P times the probability vector Px. So the vector that contains the probability that y takes on the value y1, y2, y3 up to yw is equal to P times the probability that x takes on the value x1, x2, up, and so on. And then we have the probability that y is equal to yj is equal to the sum by marginalizing over xi and yj over all possible i's, and using Bayes' theorem, this is the conditional channel probability P of yj given xi times P of xi. So essentially this matrix multiplication. Okay, with this, we can now start calculating the different components of the mutual information. And we start from the definition that the mutual information is h of y minus h of y given x. This turns out to be the very simple one for the calculation. So we start with calculating h of y. And first we say that we have a vector containing w1s. That's for convenience. So we start from the definition of h of y. H of y is equal to the sum over probability of yj times log 2 probability of yj. And we know that the p of yj is equal, can be written as p times px. So this is equal to a dot product of a vector containing the py's and the vector containing log 2 of py's. Right, this is a dot product. This is p times px transposed times p times px, where we apply the log 2 element-wise. And we can rewrite this using the so-called entropy function as 1 divided by log 2 times this vector containing only ones times the entropy function of p times px. What is the entropy function, you may ask? The entropy function is a function that's frequently contained in numerical optimization software, and we're going to express it in terms of the entropy function. So the entropy function is the following. So the entropy function is defined in the following way. So it's a function from Rv to Rv. So it takes a vector of W entries and it computes a vector of W entries. And each entry is computed as minus pi times log of natural logarithm of pi. So if we feed in a vector p, then the first coordinate we calculate minus pi times log of pi, second coordinate calculate minus p2 times log of p2, third coordinate we calculate minus p3 times log of p3, and so on. And we use this function because it's built into many software packages. Okay, so next we calculate the conditional entropy h of y given x. So we start with the definition of the conditional entropy, which is the sum over all possible combinations of x and y of the joint probability p of x I yj times log 2 of the conditional probability p of yj given xi. Using Bayes' theorem, we can convert the first part to p of xi times p of yj given xi. And then we want to optimize p of xi, so we can take it out of the first sum, where we just optimize sum over all possible xi's. Then we have a sum over p of yj given xi times log 2 of p of yj given xi. Now we define a matrix p tilde. Matrix p tilde is the so-called Hadamard product or element-wise product of p times log 2 of p. So essentially this Hadamard product is dot star that you may know from MATLAB. Essentially we take two matrices of same size and we just go ahead and we multiply those element-wise. And here we take p and multiply it element-wise with log 2 of p. So this matrix p tilde would look something like this. So in the upper right corner we have p of y1 given x1 times log 2 of p of y1 given x1. Then in the upper right corner we have p of y1 given xv times log 2 of p of y1 given xv. Then in the bottom left corner we have p of yw given x1 times log 2 of p of yw given x1. And in the bottom right corner, we have p of yw given xv times log 2 of p of yw given xv. So that's the matrix p tilde. Now we can formalize, or we can formulate the conditional entropy in terms of matrix multiplication of our unknown vector px and p tilde. So here we see that we need to sum over all yj of p of yj given xi times log 2 p of yj given xi. And that's the same as summing up over the different columns of p tilde. So we sum over all possible y's for a certain xi, and that's summing up over these rows of y tilde, and we do this for every column. How can we achieve this? We can achieve this easily by just taking a vector of w1s, a row vector of w1s, and multiplying it with p. So we have a row vector of w1s, we multiply it with p, and that just amounts to summing up all rows in every column of p tilde. And then we get a row vector that contains the sums of the different rows in every entry. And then we need to multiply this with p of xi and sum up over all xi's, and that's just the dot product. So that's meanings we take this result after taking p tilde, multiplying it with the ones, and then we multiply it with px. And that's the conditional entropy. So now we have a simple linear algebra expression for the conditional entropy. Now we can go ahead, we can plug everything together, and we get an expression for the mutual information. So it is h of y. We saw that h of y is 1 over log 2 times the vector of w1s times the entropy function applied to p times px. That's the h of y minus h of y given x. And we just saw h of y given x is 1 vector times p tilde times px. Two minus signs become a plus. So now we have an expression of the mutual information. The unknown is px. So now what we do is we just maximize the mutual information as a function of px. So we take this expression, we just reshuffle it a little bit, put this in front, and then we maximize this over px. And that gives us the capacity. Now the nice thing about this is that we can actually show, this is what you can read in the literature, or what you can, what we will derive in the AIT lecture. The mutual information is actually a concave function. Concave function means it has a unique maximum. So it's concave, it has a unique maximum, and we can find this unique maximum by convex programming. So what we do is we maximize this expression, which is the mutual information, and we maximize this with respect to this vector px, and we have a few constraints. Px is a probability vector, so px should denote probabilities, which means that px should have entries between 0 and 1, and the sum of all entries should be equal to 1. So we have a constraint saying that the sum of all entries of px must be equal to 1. And all the px should be between 0 and 1, but it suffices to say that the pxi's are larger or equal than 0. So we have positive values, or non-negative values larger or equal than 0. The sum must be equal to 1. That means there can be no entry larger than 1, because if there were an entry larger than 1, there must also be another entry that is negative, because otherwise the sum cannot be equal to 1. So these two constraints are sufficient to say that this is a probability vector, and the target function or the objective function is the mutual information. And there exist very efficient algorithms for solving this. Very classical algorithm is the so-called Blaut-Arimoto algorithm. But you can also solve this using convex optimization toolboxes, as there exist for many different programming environments or mathematical environments, software environments like Python, MATLAB, etc., as we're also going to see at the end of this video. We can now simplify this expression a little bit, and we can simplify it for a class of special channels that we already seen, weakly symmetric channels and symmetric channels. So we're looking specifically at weakly symmetric channels. So the channel is weakly symmetric. This is just a reminder. We had the definition already in chapter 1. So channel is weakly symmetric if every column of P is a permutation of every other column, and if the row sums are all equal. So here's an example. We have a channel, we have two columns, and we can see that they are permutation of each other very clearly. The row sums are all equal to 2/3. You can calculate 1/2 plus 1/6 is 2/3. 1/3 plus 1/3 is 2/3, and so on. So that's a weakly symmetric channel. For a weakly symmetric channel, calculating the capacity is actually pretty easy, and it can be calculated in the following way. So first, we pick an arbitrary column of P. We pick any one, they are just permutations of each other. We can pick an arbitrary column of the matrix P, and C is C1 to CW. And we define the entropy of this column, HC. HC is the entropy of this column. We can also express this in terms of the entropy function. And we can calculate, it turns out, that h of y given x is the entropy of this column, HC. We can do some simplifications, because HC is h of y given either x1, it's h of y given either x2, it's h of 1 given x3. Because of the symmetricity, all of these conditional probabilities are the same. And then we can calculate h of y given x, the sum over all p of xi, times h of y given xi, which is a constant hc. So we can take it in front of the summation. So it's hc times the sum over all p of xi, and it's equal to 1. So this is h of c. Okay, so we have h of c. Now we need to calculate h of y. So now we don't explicitly calculate h of y, but we say the mutual information is h of y minus h of y given x. So it's h of y minus h of c. And we want to maximize the mutual information. So what is the maximum possible mutual information? H of c is a constant. We cannot change h of c. H of y is maximized if h of y is upper bounded by log 2 of w. So this is smaller or equal than log 2 of w, and we have equality if p of y is uniform. So we have an equality if the output distribution is uniform. So when is the output distribution uniform? What is the input distribution that leads to a uniform output distribution? That's what we're going to look at next. So the output distribution is uniform if the input distribution is uniform. And this is something we can quickly check. So we can calculate p of y, the sum over p of y given xi times p of xi. P of xi is 1 over v. So we plug it in front. And this is the sum over all P of y given xi. This is a constant R. Why is it a constant? Doesn't this depend on y? No, it does not, because R is the sum of the entries in an arbitrary row of P. And this is because we have a weakly symmetric channel. Recall, in a weakly symmetric channel, all rows of P have the same sum R. So every row of R of P has a sum R, and this is exactly this expression. So this expression is a constant R because it does not depend on the row. Each row corresponds to an output symbol. It does not depend on the row. It's a constant R over V. This can only be 1 over W because this is constant. So P of Y must be uniform. So it must be 1 over W. So we can say that if we have a weakly symmetric channel, the mutual information on the capacity is maximized if the input distribution is uniform. So this is a very important result. We have the capacity of a weakly symmetric channel, this one. Capacity of a weakly symmetric channel is the maximum of the mutual information. It's log 2 of W minus H of C. And C is just one column of the matrix P. And it's achieved if P of X is 1 over V. So if every input symbol happens with probability 1 over V. So this is a very important result. It's the capacity of a weakly symmetric channel. This is something you should know by heart almost, because it's very fundamental result. It's a very important result. Log 2 of W minus H of C. Very simple to calculate. You just take the matrix P, you look at one column, and then you can do the calculation. So we can essentially compute the capacity using numerical tools. And in particular, we can use the tool of convex programming. And in our system, we have provided two software packages, one using CVXPy and one using MATLAB, using a tool called CVX package. And you can take a look at this using your own examples, and we can quickly take a look at it. For instance, at the can take a look at the Jupyter one. I just need to start Anaconda, and just give me a few seconds. I am not so well prepared for the recording, but we will get there. So let me just start Jupyter Notebook, and then we can move over there. So, and just here we go. So we can actually look at the CCGBC directory, look at code's basic concepts, and we have the DMC capacity Python notebook. That tells us how to calculate the capacity of a discrete memoryless channel, and we essentially use this tool of convex programming. So we first import CVXPy and NumPy, and then we insert also a check if a channel is weakly symmetric. So if we plug in a channel that is weakly symmetric, we would like to use the simplified equation for that one. Once we have the simplified equation, we will use the simplified equation and then we can do this check. So we have a check if a channel is weakly symmetric. So we check, we do a permutation test. If all columns are permutations of each other, we do this by sorting and comparing. And then we calculate all the row sums and check if all the row sums are equal. So we have a check if weakly symmetric channel. And then we do actually the calculation of the channel. Again, if a channel is weakly symmetric, we use the simplified equation. And if a channel is not weakly symmetric, then we calculate the optimization problem. So here, our optimization problem is different. And let me just remove this one so we have a little bit more real estate. So we can solve the optimization problem that we see here. How do we do this? This essentially turns out to be pretty simple. So it's just a few lines of code. First, if the channel is weakly symmetric, we pick a column of the matrix P, and we just pick the first one. And then we calculate log 2 of W plus the entropy of the column. So it's just the column times log 2 of the column and sum it up. That gives us P of the capacity, and P of X is the uniform distribution. So it's 1 over W. That's P of X. Now, if the channel is not weakly symmetric, the first thing we need to calculate this matrix P tilde from the lecture. P tilde is P times log 2 of P. We need to be a little bit careful because Python by default doesn't know our convention that 0 times log 2 of 0 is equal to 0. That's a convention we did, but that's not a convention that works in programming languages because that would be 0 times minus infinity. That's not a number. So we need to be careful that we only calculate the values where P is larger than 0, but then it's just the element-wise multiplication of P times log 2 of P. So then we have P tilde. Then we say that we want to optimize Px. So Px is our variable. Px is a variable. That's CP because we use a convex programming toolbox, and it has V entries. It's a very one-dimensional vector of length V. Our objective function says we want to maximize the sum of P tilde times Px. So we multiply P tilde times Px, and then we sum up. So this is the summation of P tilde times Px. Plus, we sum up over the entropy function of P times Px divided by log 2. And that's our objective function. And then we have some constraints. So the constraint is that Px should be equal to 1. The sum over Px should be equal to 1 because it's a probability. So all the probabilities should sum up to 1. And all the Px must be larger or equal than 0 because it is probability cannot be negative. It must also be between 0 and 1, but that is an implicit constraint because if one of those entries would be larger than 1, the sum cannot be equal to 1. Otherwise, at least one entry should be negative. That's not possible. And then we define the problem. So we have an objective function and we have the constraints, and we solve the problem. That's what we do. Then we can calculate the capacity of a weakly symmetric channel. And we get the capacity and the optimum input distribution. And then we can also calculate the capacity for non-symmetric channels. and we get the input distribution, for instance, like this one. We can calculate the capacity for a Z channel. So for instance, we have the probability matrix P of a Z channel, and we can calculate the capacity of the Z channel. We can do this for a range of input parameters and plot the capacity of the Z channel. And we can see this is a plot of the capacity of a Z channel as a function of Q. So if Q is equal to 0, recall the Z channel changes a 1 with probability Q into a 0. And this is the probability, if Q is equal to 0, the capacity is 1. We can in average transmit 1 bit over the channel. Q is equal to 1 means we only receive zeros. Not so useful for determining some information. So the capacity is equal to 0. And we're going to see that in detail later for the Z channel. Here we plot the probability that x is equal to 0 and x is equal to 1 as a function of Q. So this is our Python script, and you can play around with this. You're welcome to define your own channels. So just define a matrix P and then call the channel capacity, and it will give you the capacity of the channel. Good. So going back to our lecture. So we have the same not only for Jupyter, but we have also a MATLAB package. There, it doesn't work out of the box. You need to install a software that is called CVX. And then you have a very, very simple interface for optimizing such problems. Okay, with this, we reached the end of our simple introduction to information theory. What we will do next is we're looking at some specific channels and we will compute their capacity.